We are on lesson 6, sequence and series. This is going to be like your applications to geometric sequence. They call it growth and decay. Growth will be geometric sequences that increase, and decay will be geometric sequences that decrease. If you look in the structure of your notebook, there was like lesson 3 and 4 are like similar to lessons 5 and 6. They introduce the concept and then they apply it to situations in 3 and 4 with arithmetic, and then 5 and 6 here with geometric. Okay. Here we have some real life scenarios represented by a pattern of numbers which exhibit geometric growth. Okay. Okay, so here we have an article about rabbits. Starts in 2010. There are an estimated 1,500 rabbits. So I believe this first value is 1,500. Now what does it say about this population increase by 20%? If you want to increase by 20%, how to do that? What do you multiply by to increase by 20%? 1.2. Anybody have a question about 1.2? Okay, if you multiply by 1, does it change? That's multiplying by 100%. An extra 20? Okay, 1.2. So 1,500 times 1.2. Can someone yell it out? 1,800, good. Multiply that number by 1.2. Good, and one more time. Good. So each successive term is calculated by multiplying its previous term by the R value. In this case, R is 1 plus 0.2, which is 1.2. Okay. Just please put in the 1 plus. It will help you remember. Okay. Because sometimes we'll do depreciation. This is appreciation or growth, where it's 1 plus. Sometimes we'll do depreciation or decay, where it's 1 minus. And you'll see that on the next page, I think. Okay, show that the sequence is geometric. Well, we know it's geometric, but again, just to reiterate, a second term divided by its previous. A third term divided by its previous. And that will equal your R value, which is the ratio 1.2. We already know that. Okay. If term 1 in the sequence is the number of rabbits in 2010, which term of the sequence represents numbers in 2025? So these ones are always kind of to mess with your head. Okay, it's like, okay, if term 1 is 2010, then term question mark is 2025. So it might mess with your head a little bit, but if you think about it, how did we get from there to there? We had to add what? 15. So you'd have to add 15 more terms to this. So it would be T16. So understanding in these application questions which term there is specifically looking for sometimes can be half the battle. You can be good at the math, but it's like, okay, are they looking for this one? Are they looking for that one? Am I off by 1? So just be super clear which term they're looking for. In this case, it's term 16. Okay, so if the population continues to grow at this rate, estimate the rabbit population in January 2025. So we are just looking for term 16. That's all we're looking for. So we know n is 16. What else do we know? What do we know A to be? 1,500. And what do we know R to be? 1.2. So this one's just strictly plug and play. You are searching for Tn, in this case n being 16. So term 16 is the A value, 1,500, multiplied by the R value, raised to n minus 1. So 16 minus 1. Hopefully this makes sense, because you would, in order to get from term 1 to term 16, you would have to multiply by 1.2 15 times. Question? I apologize. How long did you have your hand up for? You're a good sport. Yes, this one is empty, and there's a solution manual with it. All right, so pump this into our calculator, and we're getting like 23,110, and then 0.5 of a rabbit. So can't have a 0.5 of a rabbit, so we'll just truncate it off like that, okay? No mutant rabbits. Fill in the blank, it's 1.2. Let's go to the next page. Okay, so that last page was growth. Now we're into decay. Okay, so for decay, we're looking for 1 minus something, or 100% minus some percent. Okay, so here Vinny, he's borrowing 10 grand from his parents. He's got to pay it back. They agree on a payment scheme saying Vinny will owe 10% less at the end of a particular year. This repayment scheme lasts for 8 years. At the end of the 8 years, he makes one final payment to pay off the loan. Okay, so at the end of year 1, how much will he owe? If he starts at 10,000, that's at the beginning of year 1. That's at the beginning. But we want to know at the end. See? At the end of year 1. So he would lose 10%. So how to find that? How much does he lose? 10%. So we're looking for, I'll just see where I have that 1 minus. I'm just going to quickly make a quick adjustment to that. It's going to be 100%. It's not growth, so we don't add a percent. It's decay, so we subtract a percent. How much percent are we subtracting? 10. So how much is he maintaining? 90. He maintains 90% of the value into the successive year. Okay, so you would have to multiply each time by 90%, which is 0.9. Okay, so if it starts at 10,000, you times that by 0.9, you get 9,000. So that's how much he owes at the end of year 1. Be very careful when you're reading stuff. Sometimes it's like at the beginning, sometimes it's at the end. And the question we're going to do next, very confusing question, and because it has to do with before something and after something. So let's be very mindful of the language they're using here. So take our 9 grand and times that by 0.9. Take that and multiply by 0.9. And then 6561. I just copied that out of the book. Is that right? Okay. So the values form this geometric sequence. Calculate the value of the common ratio. We already know this value. I don't know how we would have got there otherwise. So 8100 over 9000 has to be the same as 7290 over 8100, and so on. It's always the next divided by the previous to get this common ratio R, which we know is 0.9. We already know that. So that's part C as well. So part D, determine how much he owes at the end of the 7th year. So here's the end of the 1st year. Here's the end of the, oh my gosh, what just happened? Sorry. Here's the end of the 2nd year. Here's the end of the 3rd year. Which one we're looking for? So we're just looking for T7, because this is T1. End of the 1st is T1. End of the 2nd is T2. So we're just looking for the end of the 7th, which is T7. And I would just play that game in my head if I was you, if I was doing a question. I just, okay, which term are they specifically asking for? 7th year. Is the 7th year T7, or is there some weird stuff going on? Just be super careful. Okay, so we need our formula. It's A times R to the n minus 1. A is 9,000. 0.9 to the power of 7 minus 1. Because we would need 6 jumps from T1 to T7. That's why it's power 6, 6 jumps. So 0.9 to the power 6, just a small number like 0.53 times 9,000. I'm getting 4782. This is a money question, so we'll communicate 2 decimals. I'm rounding that 1 decimal up because it's money. Okay, it says 969 on my calculator, but I'm going 97. It's money, so the cents. And then they have a little stop note, which you can highlight if you'd like. Okay, and I'll reiterate that for you here. R greater than 1, we have growth. R less than 1, but greater than 0. R less than 1, but greater than 0, we have decay. Has to be greater than 0 or else nothing happens. If R is 0, then you just 0, 0, 0, 0, 0. So I like class example 3 because it gives us an opportunity just to think about how we could find these R values. Okay, so in economics there's this thing called inflation, and it says that the rate of inflation, which is like the cost of living, it says it increases by 3.5% each year. So you'd have 100%, which is your standard, your normal. What's the decimal for 100? 100%. What's the decimal for 100%? 1. What happens when you multiply by 1? Nothing happens, right? So you'd stay the same. So if we wanted to increase, we'd have to add 3.5%. So that would be 1 plus 0.035. 1.035 is your growth factor. That's your growth factor that we'd call R. If you take 30-2 coming out of 20-1, you have to know this stuff. Some people take 20-1 and they find out that it's quite difficult for them. But if you stick with it and you pass, you have a really good opportunity to do well in 30-2. Okay? In my experience teaching 30-2, I've done it like 3 times in summer school. And through like, I've also done it like 5 times doing diploma prep. The kids who take 20-1 really do well in 30-2. And 30-2 does still keep lots of doors open. Okay, so if you feel like this is hard and you want to stick with it, you know, there's still light at the end of the tunnel in math 30-2. Okay, the number of fish in a lake is decreasing by 2%. So follow the same structure. It's 100%. This time not add, but minus. So it's 98%. What's the decimal for 98%? 0.98. So what that means is you're going to maintain 98% of the value. So if I had 100 fish, the next year I got 98. And the next year after that, well, I would just take 98 and multiply by 0.98. Okay, the next one, what's the key word there? Doubling, so just R is 2. Done, just like that. Value of a computer decrease, so we're going to have to subtract by 1/5. You could go to percents if you'd like. 1/5 is 20%, so you could go 100% minus 20% is 80%. Or you could stay in fractions. 100% would be 5 out of 5. You're going to lose 1 out of 5, so you'd maintain 4 out of 5. So that's one way you could have your R value expressed. You can see here 4/5 is less than 1, so you would decrease. You would decay, just like it says up in by the stop note. And now a ball rebounding to 3/4 of its previous height. Well, if it rebounds to 3/4 of literally means times 3/4. So R is 3/4. 3/4 of. So if I was at 100 meters, the next jump I'd be at 75. Okay, and now this question. This question is challenging, to say the least. I remember actually doing it back in the day when I was in this course. It's a challenging question. And it's mostly just challenging because of the wording. And they want us to do it two different ways, and I don't really feel like doing it two different ways. Kind of just want to do it one way. But I'll try. Okay, so you're going to have to draw a picture. So we'll just read it here. You got a ball bouncing. It starts at the top of a 20-meter building. So you can just draw in a little building there. It's 20 meters tall. There's your building. So it says each time the ball bounces, it bounces back up to 80% of its previous height. So this ball is going to fall, and you have here your first bounce. And then it's going to come back up, obviously because of loss of energy. It's going to have, in this case, 80% of its previous height. So you would go 20 times 0.8, and you would arrive at 16. And then you have your second bounce. And because of loss of energy, you would take 16, in this case, times by 0.8 and get 12.8. Okay? And now what this book will do, and it has this Lucasito, whatever that is, some person. He starts the sequence at T1 equals 20. Okay? And that is before the first bounce. If T1 is 20, you're talking about before the first bounce. Now, Nicolette here, down in part B, she argues some other thing and says that I don't want the first term to be 20. She wants the first term to be 16. That's what Nicolette wants. So there's some confusion about, okay, is 20 the first term or is 16 the first term? Okay, and the reason she wants that is it's after the first bounce. Okay, and if you look up at the question, they want the height of the ball after the 15th bounce. So which one would you go with, Lucasito or Nicolette?
Wasn't technically like, because they're coming after the first bounce, right? So like, the ball's dropped from that height, and the ball's still technically dropped with the counting of the bounce.
Yeah, they want to know
So, and Nicolette,
the question, and this is like what you guys have to deal with in a test situation, is this very specific, they want a very specific value. It might be like a numeric response or something. There's no leeway, right? So it says you need to calculate the height of the ball after the 15th bounce. So which one do you want to go with?
Nicolette.
Yeah, I would go with Nicolette. Because after the first bounce, you come up here and you can call this T1. So for Nicolette, you would solve for T15. 15th bounce, T15. Is that confusing? No. T15, 15th bounce. But if you go with Lucasito, you're actually not looking for T15, you're looking for T16. And to me, that's just confusing. Because T16 is after, for him, this is T1. It's before the first bounce. It's like T0 though, but T0 doesn't really exist, so we can't really use T0. It is like T0, yeah. So I'm just going with Nicolette here. I don't like Lucasito's start here. I would just be, and then the only thing that I can offer to you guys is be super clear about what's being expected, and then how you are thinking in your head. Do you really understand which term you're going after? Okay? So I'm not going to go with Lucasito's method. I'm going to go with Nicolette. Okay. Okay, T15 is your A value. The first term for Nicolette is 16. Each successive bounce goes to 0.8 of the previous. And how many times would we have to do this if it's T15? 15 minus 1 for 14. Good. So 0.8 to the 14. And then timesing by 16, I'm getting 0.7036, whatever, meters. Does it want centimeters? To the nearest centimeter, good reading. So times this by 100, because there's 100 centimeters in every meter. You divide by 100. Okay, make sure you guys know your metric, okay? So it's about 70 centimeters. Okay, so we're not going to worry about C. We didn't worry about Lucasito. And it says, write an equation which could be solved to determine the minimum number of bounces required for the rebound height to be less than 2. So let's go with Nicolette, right from the formula sheet. We have Tn equals 16, 0.8, and minus 1. This is our formula. Is there anybody that disagrees with this or is confused about this? So after n bounces, it calculates the height after the bounce. This is our formula. Now, this is where some kids are having confusions from a couple days ago. Hopefully it's resolved. Where does this 2 go? The Tn or the n? This is a Tn. Good, so 2 equals 16.8 and minus 1. So, thank you. I tend to do that. I forget about units. So, Chi Ming brought up a good point. Why is it not 2? Because our calculation is in meters, right? So all this, do I have a yellow pen? That's in meters. So this has to be in meters on the left-hand side. So this is going to be 0.02. Okay, now in general, in math, to solve a problem that has a variable in the exponent like this, you have to use this thing called the logarithm, which we don't have yet. That's a Math 30 thing. So we're going to use our calculators. Our graphing calculators will actually solve this for us. Okay? So go ahead and take those out. Okay. Compound interest is in economics as well. Everybody in the world for finance uses compound interest. If you know about simple interest, it's not even used in real life. So we're going to develop this compound interest idea using sequences. So here Mike invests $5,000 into a GIC, which is just an investment fund. So at 3% interest is added to the value of the investment at the beginning of that year. So it says consider the geometric sequence which represents the value of the investment at the end of each year. State the growth factor. Okay, so if you have $5,000, how are you going to get the next amount of money in an investment. In this case, we are growing by 3%. So what do we multiply here? 1 point something for sure. So it's got to be slightly bigger than 1 to make it grow. The 0.3. Okay? Yeah, that's true. Okay? So this is your R value here. This is your R value. So again, with this T0 business, depending on how you look at it, so how do we look at this one? Everything's always case by case. So it says at the end of each year. Okay? So what does that mean? So what's T1? Is T1 5,000 or is it 5150? Yeah, so it's 5150. So what would T2 be? It would be 5150 times 1.03. But check this out. We already know what 5150 is. That was 5150 is all this, right? So let's just substitute that back in. 5,000, 1.03, 1.03. So to get to the second year, the second term, you would start at 5,000 and multiply by that R value twice. So this one's compound interest is a little bit different than your standard sequence formula. This should be weird to you at this point. So all this is down in here for part C. Because it says for part C, write a product which represents the value of the investment after 2 years. So that would be T2. But T2, you would have to subtract 1 from that. So this should not make sense to you. This should be contradicting what we already know. Right? Shouldn't T2 be this? So you should have a 1 in the power? Yeah, and it's all because of this 5,000 starting point, and it's just weird, okay? So I'm going to skip a lot of this nonsense, because it's just nonsense, and I will show you the compound interest formula. That you need to know for this course. It's a little bit different in real life, but for this course, this is all you need to know. And I would just memorize this compound interest formula. Okay? So the compound interest formula, which they call A, for just like maybe like accrued amount, or maybe it's amount, I'm not sure why they use A. But P is your principal, that's your starting amount. And you're going to multiply it by a factor that's always going to be 1 plus. And we know why it's 1, right? That's the 100%, right? Plus some interest rate, but it has to be a decimal. So if it's 5%, it's 5 divided by 100, which is 0.05. This is just 1.05. If it's 10%, this is 1.1. If it's 7%, 1.07. You with me on that? Okay. I will tell you. Okay, so you had a question about the unit exam or the final exam? Let's just let the seconds take care of the minutes. Let's do the unit exam. So on the Wednesday of next week, we're going to do a practice test. So on the Wednesday, I will write down a study sheet for you guys. If you want to get started on your study sheet now, that's okay, but I'll help you with the first one on Wednesday. You can always get it started now if you wanted. And on Wednesday, I'll give you an idea of what will be on your exam so you can prep for it Thursday night for your exam Friday. I'll probably start the new unit on Thursday. next week. So Wednesday will be the practice test. Okay, and then I'll give you the homework, and then it's going to be the East block here.